This is part 2 for the Chapter 15 lecture. So I just went over the bits of information that are included in the Pearson correlation value. So Pearson correlation is represented by the letter R. So anytime you see the R symbol and then like R is equal to 1 would be an example of a positive perfect correlation. So we just went over in the last part of the lecture the fact that anytime you're looking at your R value, it gives you information about the direction of the relationship. So if it's positive, it's a positive correlation. If it's a negative correlation. Also, the numerical value in your correlation, it tells you the strength of the relationship. So I have several different examples of correlations here, and we're going to go through these examples to get a better understanding of what different correlations might look like. So in this example, we have our data points here. And if we look at the line that best describes kind of the general trend of these data points, it might be something like that. So you should be able to tell already that this is a positive correlation. So it's a positive correlation because the tilt of that line is going up in that higher or positive direction. Also, high scores on X are associated with high scores on Y. So you should see by that trend line, since that line is slanting up, that's a positive correlation. The actual numerical value of the correlation is dependent on essentially whether these dots are data points, whether those are falling exactly straight on this line, or whether they're kind of far away from the line. So the closer our data points are to this line, the stronger the correlation is. So this example here is going to be a correlation of 0.94. So you'll see that our data points are fairly close to the line, but they're not perfectly on it. So if they were perfectly on the line, then it would be a correlation of +1, but they're deviating just slightly from the line. So essentially, the closer your data points are to that line, the stronger your correlation is, or the closer to 1 it will be. So let's go through another example. So here we have some data points. You should be able to tell just looking at these data points that this is going to be a negative correlation. So those data points generally fit this trend where we see this downward slope of our data. So many of our data points actually are fitting on this line, but there are several data points that are deviating from it. So it's certainly not a perfect correlation because not all the data points are falling on that straight line, but it's fairly close to 1. So the actual number for this correlation is -0.89. So it's a very strong negative correlation, but not perfect. Let's try this one. So here's another example. We have a whole bunch of data points that are kind of all over the place. So in looking at this, it's actually quite difficult to make sense of these data points. There doesn't seem to be any kind of consistent trend, almost like if this one didn't exist, if these two didn't exist, maybe it would be a positive trend, but it's hard to find a line that best describes all of these data. And the reason for that is because this is essentially a non-existent correlation. So this is a correlation value that's quite close to 0. So it's just 0.11. So while it is technically a positive correlation, it's not a very strong relationship. So again, the strength of the relationship would be the degree to which your data points are falling on a straight line that's either slanted up or slanted down. So since we can't really make sense of these data points, it's hard to find a general trend in them in the first place. And again, the reason for that is because there's not a very strong correlation between these, the X and Y variable in these data. So let's try another example. So here, we can see that these data points, they follow this general trend of, low values of X or low scores on X tend to be associated with higher values on Y. high values on X seem to be associated with lower values on Y. You try and find a line that might best explain that data. It might look something like that. But we'll notice that with this example, our data points aren't really falling as close to the line as we would anticipate them to. So essentially, since each of these data points, yeah, they're following that general trend downward, but they're kind of spread out far away from that line. So this would be a correlation of negative 0.68. So again, the negative refers to the fact that these two variables are negatively correlated. So we see that downward slope in the data, where high values on one are associated with low values on the other. So that's a negative correlation. It's still fairly strong, so it's still kind of closer to the line, but not as close as those 0.8 or 0.9 correlations were. So the further away our data points are getting from this line, the less strong our correlation is. So that's a smaller numerical value representing the lower strength than some of the other ones, like the 0.9 correlations. Let's try one more example. Here we have our data points. Again, these data points are a little bit more spread out than some of the other examples that we had at the beginning. But you should be able to see there is kind of like a general trend upward here, in that we got some low values of X are associated with fairly low values of Y. And especially over here on our high value of X, seems to be associated with a high value of Y as well. So this has this same trend of a positive correlation, in that high values of one are associated with high values on the other, low values of one are associated with low values on the other. But again, we have our data points that are straying kind of far from that line. So since those data points are a little bit further from that line, this would be a less strong correlation than like the 8.8 or 0.9 correlations. So this is an example of a correlation of 0.53. So again, it's a positive correlation because it's not a negative sign. And then we have the 0.53 refers to the strength. So still, it's a fairly strong correlation, but just not as strong as some of those like example 1 and example 2. So some other things that I want y'all to remember when we're dealing with correlations, and this first one is a huge one, is that correlation does not imply causation. So you have to remember, anytime you're dealing with correlational findings, you never, ever, ever want to say cause, effect, any words like that that imply that type of association. And so for that, we use very specific terms when we're referring to correlational findings. And so in general, you'll notice this when we're talking about the conclusion in this chapter, but in general, when we're talking about correlations, we always use one of these words to describe them. So we would either talk about the relationship between variables, we might talk about it as a correlation between two variables, that one seems pretty obvious, or we might also use the word association. We would never use the words effect, affect, any of those, because those imply a cause and effect relationship, but correlational analyses always just involve the measurement of two variables and seeing if those two variables are related. So since correlational studies never involve manipulation, we would not ever talk about the findings from those studies in a cause and effect sort of way. So another thing to keep in mind when we're dealing with correlational findings or correlational analyses in general is that the value of your correlation can actually be very, very affected by the range of scores that are in your data set. So let's say that we're interested in looking at the relationship or the correlation between age and driving ability. And so in order to test that, let's say we take a sample of, people in high school and college between the ages of 16 and 25. So if our sample involves 16 to 25-year-olds, we'll probably see this trend in our data And you should be able to tell in this trend in our data set, this is representing a positive correlation. So we see that in general, as age is going up, so is driving ability. So in this sample of students, so the range of age is from 16 to 25. In this sample, we see that there's a positive correlation between age and driving ability. However, there's probably something that's being left out here of the whole story. So if your conclusion here was that that there's a positive correlation between age and driving ability, that might not be super accurate, because as you see, we have only the ages of 16 to 25. So if we were to broaden our sample a little bit, and let's say instead we collect data from another sample, that sample being 25 to 90, let's see what our data might look like. So again, taking the same example of a correlation between age and driving ability, if our sample is ranging from 25 to 90 years old, our data looks quite different here, in that you'll see that you should be able to identify this now as a negative correlation, in that people that are low in this age have a high driving ability, and then people that are high in this age range have a low driving ability. And so now with this new range of ages, this is now a negative correlation. So if we had either of these two limited samples, that would lead us to the wrong conclusion. In reality, the relationship between age and driving ability, had we had a full data set with all of the possible age ranges, let's say ranging from 16 to 90, the reality of that would be that it's a curvilinear relationship. So a curvilinear relationship basically refers to the fact that, as from 16 to 25, the relationship between age and driving ability goes up. It's a positive relationship. And then once you hit the age of 25, and I made up all these data, but once you hit the age of 25, then your driving ability might start to decline. So a curvilinear relationship is a little bit beyond the scope of what we're going to be talking about for the rest of this chapter, but do know that it's possible, such that, had we only had the range of 16 to 25, it would have greatly affected that range of our correlation. So some other things to consider when we're dealing with correlations is that outliers can have an extremely large effect on the value of our correlation. So in this sample here, we actually don't have any outliers. So in this sample, there are no outliers. And the only reason I'm showing you this data is so that we can see the effect of if an outlier was added to these data. So here we have the correlation, and again, I made up these data, but we have the correlation between the number of times married and the number of children people have. So here we see that, yeah, there is a positive correlation in these data, but that correlation is not too strong in that it's only 0.22. So not an extremely strong correlation here. So these are the data without any outliers. But let's say that we had an outlier within this sample of a person that had been married 100 times and had 100 children. Again, I made these data up just for the purposes of showing you what this would do to our correlation. So here's the data from before in that last slide with just those people who ranged from 1 to 5 on each of those two variables. And with the addition of this outlier, we have that positive trend in our data, but just adding that one extreme score, that outlier. So an outlier is basically just somebody that's extremely different from the rest. So by just adding that one extreme outlier, that changes our correlation to actually be bigger than 0.99, which is almost a perfect correlation. As you can see in these data, they're definitely not perfectly correlated. So that outlier had a great effect on the value of our correlation in a problematic